All right, guys, so we're going to look at the electric field due to a continuous distribution of charge. So far, we've just done things like point charges or a spherical charge. And the nice thing about that symmetry was, we were able to define the electric field everywhere in space around that charge. And the reason is, there's really a lot of nice symmetry there, and that is if you draw a circle or a sphere around this point charge, everywhere, every point on that sphere, every point on that circle is the same distance away from that point charge, right? So when you say that the electric field from that point charge or from that spherical charge is kq over r squared, you were defining all the space a distance of r away from that positive charge. And then you get an idea of what that electric field looks like. If you drew a bigger circle, a bigger circle, a bigger circle, you know that the electric field is just proportional to 1 over r squared. So you could say the electric field looks something like this. Electric field with respect to the distance away from your point charge, it is, again, proportional to a 1 over r squared. It looks something like that. Okay? Proportional to 1 over r squared. And then we did the same thing for a negative charge. Again, we could say that anywhere, any spheres around this point charge or any spheres around that circle are going to give you an electric field that is proportional to 1 over r squared. The only difference for a negative charge is when we defined this electric field in this space, we said, well, if you use a positive test charge would be attracted to a negative charge, so we drew the electric field lines this way, and that was our conceptualization of that electric field. Okay, so when we did point charges, we were defining all of the space around that. But now when we get into a little bit more complicated geometries, we get into some, maybe you've got some weird mass of charge, and it's got a total charge of plus q. Well, the electric field is going to look weird. It's going to look different because this is not a very symmetric object. The one thing we can say is that electric field lines are perpendicular to the surface of the object. So along all of these curves, you could do things like drawing the electric field perpendicular, and you could go again. You go the whole way around this electric, this weird continuous distribution, just making sure that your electric field lines are perpendicular to the surface, right? But that's not very exact, and I haven't done any math, and all that really does is give me the general shape of the electric field. It doesn't give me a magnitude of the electric field anywhere in this space around that charge, okay? So why is it that the electric field is perpendicular to the surface? Well, if this were a conductor, you know that charges are free to move around anywhere they want on this conductor. And in a static situation, they're going to move themselves to the edges to get as far away as possible, to get to the lowest possible energy state of this continuous distribution of charge. So you think about the electric field lines. Well, if, for example, you had an electric field line at the surface of the conductor that was not perpendicular to the surface. Okay, let's just assume that is a possibility. Well, you have that electric field line, and you say, okay, this electric field line has one component at that surface. One component is tangent to the line, and a second component is perpendicular, right? So this is the purple one. That was our claim that the electric field would only be perpendicular. Why would we not also have, the possibility of a parallel component? Well, if you're a positive charge, and there is a component of the electric field this way, parallel to the surface right there, then that positive charge is going to start moving along that electric field line. And that's not an electrostatic situation. So just by the definition, just by saying that we're doing electrostatics, it means that on this conductor, the electric field has to be perpendicular at the surface. Okay, so all the charges go to the outside, and in a static situation, the electric field lines are all perpendicular to the outside. Okay, now of course, in order to find the electric field in this space around the charge distribution, then I would need to select a whole bunch of little tiny DQs, right? This thing is made up of a whole bunch of little tiny DQs. And if you wanted to find the electric field out in this space, you would add up the contribution from each of these charges. Well, unfortunately, there's not a beautiful symmetry, a spherical symmetry like we had for point charges. I can't imagine picking any point in space where the distance from each of these point charges is going to be the same. Right? I can't imagine any space where that would be true. So when we do a continuous distribution, instead of being able to define the electric field and the magnitude of the electric field in all the space around this charge distribution, unfortunately we are kind of limited to just saying, okay, what is the electric field here at this point? And that would then say, okay, if I place a charge there, what is that charge going to feel? I don't have as much freedom to define all of the space around the charge. I can only find it at specific points. And hopefully when we look at some of these things, we'll get some shapes that do have some symmetry so that we can define the electric field a little bit better in the space. But if you have something totally random like this shape right here, it's going to be pretty challenging. You're only going to be able to get the electric field at certain points in space, not to be able to define it as a function of R. Okay? So in order to find the total electric field at point P, what I want is the electric field at point P. Okay, but you'll notice that it is a different distance from every charge that exists in this charge distribution. So what I would have to do is I would have to set up an integral or an infinite sum that says, in order to get the total electric field at point P, I would have to add up the contribution to the electric field of all the little tiny point charges. Okay? And that would be from 0 to the total electric field at point P. And in order to gather the contribution of every one of these little tiny DQs, then I would just add up their point charge contribution. But we know that a point charge contributes KQ over R squared. The difficulty is that each of these charges would have a different R value. Okay, so when I'm writing this integral, I've got K times Q, but they're little tiny point charges, divided by R squared. And the instant that I write that down, I notice that I have a problem because R is a variable. Every charge would have a different R, and Q is my small factor. So just like when we did moment of inertia, and you wrote something like this, the integral of R squared dm, the moment you wrote that down, you realized you had a problem because R does not match M, so you knew that you had to do a change of variables here. And we're looking at the same sort of situation here. If R is a variable, if all the charges are a different distance away from point P, then I have to find a way to change this small factor into dr instead of dq. Okay? And the way that I'm going to do that is, number one, I'm going to assume that they are giving us a continuous, uniform distribution. A continuous uniform distribution. That means that the charges are evenly spaced out. They're evenly arranged in this, in whatever this weird shape is. They're uniformly distributed. That's going to simplify things slightly. The same way we did with masses in moment of inertia, we wrote down densities, but now these are going to be called charge densities. Charge densities. In one dimension, if we have something like a bar or a wire, we're going to use lambda for charge density, and that would be total charge divided by total length. What that means is, for this bar or one-dimensional object that has charges uniformly distributed along it, okay, plus. If they're uniformly distributed, it means that any chunk of this bar that I cut would have the same ratio of charge to length. Any length that I cut would have the same ratio of charge to length. Okay? And then in 2 dimensions, we're going to use sigma, and that ratio then becomes charge to area. So any area chunk that you pull off of a 2-dimensional shape with a uniform distribution, the ratio of charge in that chunk divided by the area of the chunk should be a constant. And in 3 dimensions, we're going to use rho, and that is charge per volume. Okay? So what I'm going to do then for any of these continuous distributions, I'm going to find a way to rewrite dq in terms of the distance that each point charge is away from my point P. Okay, so what I would do then is I would rewrite again the electric field at point P is equal to the integral of all the little tiny contributions to the electric field from 0 to EP is equal to the integral of k dq over r squared, but I'm trying to find a way to make these match. So I would write something, let's say we're doing a 1-dimensional shape, I would write something like this. I would say, okay, if lambda is the ratio of charge to length for any length of that object, total charge over total length should equal, well, if I just pull out one little point charge, if I were able to cut that out of my bar, if I just cut out one little point charge out of my bar, the length of that little cut that I made, we'll call that dx. The ratio of dq to dx should be the same as the ratio of total charge to total length. Because again, we said this was uniformly distributed. So then it does give me an opportunity to rewrite dq. dq is lambda dx. And then again, in the case of 1 dimension, not having a second or a third dimension to go to, I would change this r then to be an x if I'm only looking in 1 dimension. Okay, so what we're going to do next is we're going to look at some of the most common distributions of charge that we'll see in AP. I'll give you the 4 that are highly likely and are sort of the expected ones for you to see on the exam so that you'll be prepared. Okay.